Okay, so kind of talked about this a little bit yesterday. So what we're really just going to go over is just a little bit more of 3.4. So we can call this 3.4b. So tables, your book isn't really big about tables, but the AP test is. So this is why we kind of have this, and you'll see some on the worksheet that have to do with this. And so we have this table, there's the x's, we have f, f prime, and f double prime. We won't necessarily use all the information, especially on any given problem. So on part A, it says, is there a value of x where f of x must equal 0? So I'm thinking, let's look at the f row. Now, I don't see any place where f equals 0, but if we have a continuous differentiable closed interval graph, I can apply any of my theorems. So first of all, do y'all think there has to be f of x equals 0? Yes, why? Yeah, so somewhere right in here, 0 has to be between -2 and 1. And that word between should kind of give you a hint as to which interval or which theorem I'm talking about. So which theorem is all about betweenness? Intermediate value theorem. So by intermediate value theorem, watch what I'm going to write here. -2 is less than 0 is less than 1. So first of all, we just show in a concise way that 0 is between these two numbers. I could have just as easily picked 5 and -2, by the way. Okay, I just picked these two. I do need to relate it back to the function. So I need to list, okay, how is -2 part of the function? It's f of 0. And 1 is f of 1. So what I've shown here is that 0 is between f of 0 and f of 1. Okay, that's all I need to show. The rest is done when I quote intermediate value theorem. So there must be a value, or I'm not going to get that technical. There is a value of x on, and I'm going to go ahead and list just the interval I'm talking about, 0 to 1. That's what I'm showing, and so that definitely then takes care of the bigger interval, where f of x equals 0. Okay? So if we look at B, it's a very similar problem, except this time it says f prime equals 0. So if we look at f prime row, do you see a place where f prime is 0? Yes, so that would actually be the easiest way of explaining this problem. Yes, f prime of 2 equals 0. Okay, so we could definitely say that. Yes, f prime of 2 equals 0. Just for fun, right? Because what else is fun when more than half the class is gone on a Friday afternoon than to do more work? So what else could I do? What could I do with intermediate value theorem to prove, like, let's say this 0 had not been there. Is it implied that 0 is going to happen at some place in between 3 and -1? Yes, so I could have done something very similar as part A. All right, let's say I didn't know this row at all. Let's say I had no clue that anything in that row was there. Okay, this is the real fun part. I'll just wait. All right, you prepared? How can I just use the f of x row to prove this? And think about our other two theorems here. So what are our other two theorems besides IVT?
EVT.
EVT, extreme value theorem. That doesn't really, I don't really care about absolute max and min. So what's the other one? MVT. So with MVT, that has to do with where the average rate of change equals the instantaneous rate of change. F of 3 minus f of 0 over 3 minus 0. That is the average rate of change. What does that equal? What is f of 3? -2. What's f of 0? So I'm going to write +2. What does that equal? The whole thing. 0. So if the average rate of change is 0, then what else should equal 0? IROC, which is f prime of x. So this is a totally different way of doing the problem. I really showed y'all 3 totally different ways of doing it. Let's move on to the next one. Okay, C, does f of x have any point of inflection? And so I'm going to go back and erase this stuff because we may need it. Point of inflection. What does point of inflection mean? And let's look at f double prime here. What would have to happen with f double prime? We would have to change signs. Does f double prime change signs? Yes. So let's write it. Yes. F double prime of x changes signs. And if so, at what value of x? Do we know the answer to that? This looks like a pretty good candidate right there. Right? Isn't that how we even found points of inflection? We found where the second derivative equals 0. However, I could be going from 2 to 0, and couldn't I, after 0, go back to positive, and then later on go negative? So I really don't know that that's a point of inflection. If so, at what values of x? All we can really say for this is we're not, I can spell the word sure. Not sure, well, whatever. Not sure of exact value. But I know that it's happening. I know that it's happening somewhere between 0 and 2. Okay, and let's pretend when Miss Brooks did this that she didn't repeat and say point of inflection twice. Let's say she said relative extrema. So what would we be looking for relative extrema? The changes in f prime, so does f prime change signs? Yes, so let's write that. Yes, f prime of x changes signs. So now let's see if we can get a little bit more detailed. We can actually figure out the value of x, and we can tell if it's a max or a min. So what do you guys think? First look where f prime equals 0. That's a possible, or undefined, right? But this right now is only a possible relative extrema. Okay? But I know that if f prime equals 0, and so watch this, f prime of 2 equals 0, and f double prime of 2, what does that equal? Negative 3. So I'm just going to write less than 0. So can you guys remind me when the first derivative is 0 and the second derivative is negative, aka concave down? Where is the first derivative 0 again on this picture? Right there, which we call a relative max. So we can be sure there's a relative max at x equals 2. And that's the second derivative test that we learned about yesterday. Okay, so that was just a few examples kind of off of a table, some old stuff, some new stuff. One more example. You ready? Okay, first part is review. So go ahead and do that part on your own. Write the equation of the tangent line at x equals 1. There's your f of x right there. What do you need to write an equation of a tangent line? A point and a slope. So we got the x value. You go back to the original to find the y value, and what'd you get? So if we go 1 plus 5 minus 3, that should be 3. It's okay. All mistakes are forgiven. It is Friday afternoon and half the class is gone. All right, slope. What do we need to do slope? We need the derivative. So we got to find that derivative. Remember, that's going to be a part of the problem on most examples. If you're ever stuck, find the derivative. And you get 13. So my tangent line, y minus 3 equals 13, x minus 1. And that's something we've already done. Okay, lots of times. Part B, we did one time weeks ago. So you probably don't remember, so I'm going to go over it. use the line from part A to approximate the value of f of 1.1. So to find the true value, let me just do this off to the side, f of 1.1, we would actually have to plug in 1.1. Do you want to do this without a calculator? No. Okay? And this is all going to be stuff on no calculator parts. So that's why that word approximate is there. So what we do first is we take our tangent line and we get y by itself. So I'm going to add 3 to the other side. I'm not going to distribute through the 13 though. We really don't need to do that. So I just added 3 to the end. F of 1.1 is going to be about, use the tangent line now to plug in 1.1. We still got to do a little bit of number crunching, but it's a lot easier. Now, you can leave your answer like that. For purposes of like at the end checking it, I want to go ahead and figure out what this equals. So like 1.1 minus 1, that's 0.1. And 0.1, to multiply, you just move the decimal. So 13 times 0.1 is 1.3. And then you add a 3 to that, and you get 4.3. So this is our approximate value. All right, now something new I haven't asked you yet is our approximation over or under? Why do you say that? What? You have a 50-50 chance. So I'm going to say this has to do with concavity. So just follow me here and I'm going to explain it as we go. If we find the second derivative, which ends up being 6x plus 10, and we evaluate the second derivative at that x value. In fact, I don't even care about what it equals. All I care here is about concavity. So can you be pretty sure that the second derivative at 1.1 is positive? If you plugged in 1.1, you would get a positive value. So what does that tell us about concavity? Concave up. So look what happens when I draw a concave up picture. So that's our little sketch of f of x. Let's say 1 is right here. And so I drew a tangent line. Okay, and so that's where 1 is. Right there is the true value of f of 1.1. Down here is the approximate value. Okay? So this is why this works. If you have a curve and you have a tangent line at say 1, 1.1 is going to be really close to that point. And plugging in 1.1 into the tangent line is a lot easier than plugging it into the messy f of x function. We can do that in our head. We can't necessarily do 1.1. It wouldn't be impossible, but on some problems it could be really difficult. Okay? And a tangent line is always going to be a line. And so see where that tangent line is? It's under the curve. Why is it under the curve? Because concave up. So this was an under approximation. It was an under approximation because the graph was concave up. And the only way I knew that is to analyze the second derivative at that x value. So what do you think would happen if we had a concave down problem? I mean, think about it. If it was concave down, where would that tangent line be? It would be above, and we would have an over approximation. Whoops. There we go. So this is kind of the general rule. You don't have to memorize that. You can always look at a picture. So I